This video is going to talk about cofunction identities, and I have written here two cofunctions, kind of our most basic original trig functions that you learned back in geometry, sine and cosine. And we've seen these before. We've actually proven these identities using angle difference formulas, using sine of alpha minus beta, and then expanding that out, and eventually simplifying that down to cosine of theta. So now we're going to think about this kind of another way, using what we learned back in geometry and what we talked about in the last video, where we talked about the acute angles adding up to 90 degrees, which if you think about this in terms of radians, that's pi over 2 radians. So here I've drawn a triangle. This is a special right triangle, 30, 60, 90 triangle, just to kind of keep this basic and familiar to us. And I'm going to label these sides A, B, and C. And I want to write two trig ratios here. So for starters, I want to talk about sine of 60 degrees. So remember, sine is opposite over adjacent, so that would be, opposite over hypotenuse, so that would be B over C. And then let's do cosine of 30 degrees. So remember, cosine is adjacent over hypotenuse, which is B over C. So hopefully you're noticing I've got two expressions here, sine of 60 and cosine of 30, that are both equal to B over C. And that makes sense because you've already learned on your unit circle that cosine of 30 degrees, or cosine of pi over 6, is root 3 over 2, and that indeed does equal sine of 60 degrees on your unit circle. So we're kind of looking at this two different ways. Visually with this right triangle using what we learned in geometry, and then thinking about our unit circle here, this is a true statement. Both of these things equal root 3 over 2. So as a summary of what we just talked about, for this picture here, sine of angle A is opposite, which is side A, over hypotenuse, and cosine of angle B is the adjacent side over the hypotenuse, and these two things are equal to each other. Okay, so whatever angle A is, let's call it x. We don't know the measure of it, but we do know, based on what we've been talking about, is that angle B is 90 degrees minus x. Okay, so sine of 90 degrees minus angle B gives you the sine of A, or cosine of 90 minus A gives you, wait, I don't know if I said that right. Let me start over there. Sine of 90 degrees minus B, angle B, gives you angle A, and sine of A we know is equal to cosine of B. So here's kind of a general statement which we had presented initially as our cofunction identity. Same thing with cosine of 90 minus A. Remember, 90 minus A is just angle B. So cosine of angle B is the same as sine of A. That's what we wrote down here. So here's this general formula. Here's kind of a formulaic example of that, and here is a concrete example using the unit circle. So you can think of some other examples on the unit circle where sine of A equals cosine of B, where A and B are complementary angles. I gave you one that was 30 and 60, but you could use other angles. And I'd also like to mention that you can really use any complementary angles. It doesn't have to just be unit circle angles. So that's what we're about to get into. So the cofunction that we were just talking about, where sine of pi over 2 minus theta is cosine of theta, or sine of 90 degrees minus theta is cosine of theta, that idea is basically these two complementary angles that add up to 90 degrees, sine of the one angle equals cosine of its complement. So the complement of 56 degrees is 34 degrees. So these are equivalent statements. So now switching into radian mode, and we actually already talked about this example, if I want two angles that add up to pi over 2, and I'm already at pi over 3, I need to add to that pi over 6. And thinking about this in terms of what you know on the unit circle, I know this example we couldn't actually evaluate, but this one we can. We know that cosine of pi over 3 is 1/2, and we know that sine of pi over 6 is 1/2. So there we know that this is a true statement just using our knowledge of the unit circle. So we've already talked about sine and cosine being cofunctions. So here are our other two sets of cofunctions, tangent and cotangent, makes sense that they'd be co-functions, tangent and cotangent, vice versa, cotangent, tangent, secant and cosecant. So hopefully these are easy for you to remember that they're co-functions, since each is named as a word with co at the beginning. So we'll just put little hearts here to remind us that these guys are partners. So when it comes to, simplifying expressions like we're about to do, we're going to keep in mind what our partners are in co-functions. So here's our first example where we're just trying to use co-function identities to simplify an expression. So what I want you to keep in mind is that you need to get your angles to match first to be able to simplify this. And we've sort of already done things like this where we had to do things like subtract 180 degrees or subtract 360 degrees, use even and odd identities. So we're just using another identity to try to simplify things. And I want you to keep in mind that sine over cosine is equal to tangent. But we can't use that rule until we change this angle. So we can't actually do this subtraction problem. So here's the first thing we want to do. We want to worry about sine of 56 and cosine of 34. Well, earlier, we actually decided that those were equal to each other. So we can actually replace this cosine of 34 with sine of 56. Okay, so this was sort of like, it was almost like a trick question. We couldn't do tangent minus tangent because the angles didn't match. So now you see we have sine of 56 over sine of 56, and we know that that is equal to 1. So we basically end up with 1 minus tangent of 56 degrees, and that's as simplified as we can get it. We can't really do anything else with this. So this next example uses the same problem that we did above as well. You can change cosine into sine or vice versa, it doesn't matter. You could even evaluate these actually since we're able to evaluate, but let's not do that since we're trying to kind of focus on a new practice. So cosine of pi over 3, we know that that is the equivalent of sine of pi over 6. This was like our concrete example from up above. And let's not change the other one. So you don't want to change them both or you'll be right back where you started. You just want to change one, get it to match. And we know that this equals 1, so there we go. This is totally simplified. And a lot of the time, like the expressions that we were simplifying before, you probably are going to get zeros or ones. Okay, so this one is a little bit more complicated, but hopefully you're seeing this 1 minus cosine squared, and maybe you're thinking, isn't that the same as sine squared? Using that Pythagorean identity. So 1 minus cosine squared, the angle doesn't change, so that would be sine squared of 20, okay? And then the minus cosine squared 70 is going to stay the same for now. But now we're, stuck again. So what can we do? Well, we know these cofunctions. We can either change sine of 20 degrees into cosine or cosine into sine. Either way, change one, choose one. Let's change this one. So we know that sine of 20 degrees is cosine of its, or cosine squared, of its complement, which is 70 degrees. So we've got cosine of 70 degrees minus cosine squared of 70 degrees minus cosine squared of 70 degrees, and we know that something minus itself gives us 0. Okay, so our last example is a bit of a challenge. The reason being, these two angles, 7 pi over 12 and 5 pi over 12, they both add to 12 pi over 12, which is pi. So we can't use this pi over 2 complements idea quite yet. So let's try something. Let's at least subtract from 2 pi. We're going to use those cofunctions that we used previously. So I'm talking about these. Secant of pi over 2 minus x equals cosecant of x, and cosecant of pi over 2 minus x equals secant of x. So we're going to subtract 7 pi over 12 from pi over 2, which is the equivalent of 6 pi over 12. So that's going to give us negative pi over 12. And because we subtracted from pi over 2, our secant is going to change to cosecant. So we have cosecant of pi over 12. Okay, so let's do the same thing that we just did to the denominator. So we're going to do cosecant. So we're going to do pi over 2 minus, oh, sorry, I forgot my negative up here. Okay, so we're doing pi over 2 minus 5 pi over 12, which gives you positive pi over 12. And we're changing cosecant into secant. Okay, so my angles almost match here, but I've got a negative angle here. So keep in mind cosecant is 1 over sine, the reciprocal of sine. So sine is an odd function, which means that cosecant of a negative angle is the negated version of cosine of the positive angle. Okay, so we've got negative cosecant of pi over 12 over secant of pi over 12. So at least here our angles are matching, so we can at least use that to continue simplifying this. So now we really just need to think about what cosecant over secant is. So we know that cosecant is 1 over sine, and we know that secant is 1 over cosine. So we need to multiply by the reciprocal here. So we're going to keep the top the same, negative 1 over sine of pi over 12 times the reciprocal of the denominator, so cosine of pi over 12 over 1. Okay, so we get negative cosine of pi over 12 over sine of pi over 12. We're on the home stretch here, you guys. So negative cosine over sine, remember, is cotangent of pi over 12. And that's as simplified as that gets. Technically, we could use, if I wanted you to evaluate it, you could use sum and difference formulas or a half angle formula, since pi over 12 is half of pi over 6, but I'll let you stop there. Keep in mind that you could keep going, but we'll stop there since we used cofunctions to get that as simplified as possible. So on your homework questions, be prepared to use those cofunction identities with cosine and sine, changing those into one into the other, tangent and cotangent, and secant and cosecant. Be prepared to change one into the other. But also don't forget the things that you already know, like even and odd identities, Pythagorean identities. Keep in mind, be flexible. Try an approach and see if you get somewhere. And if you don't, then, try a different approach. It's sort of like when you were verifying trig identities. Be ready to be flexible.